First question is, you have worked on the communication and display systems of various space exploration programs. So let us know about your work, what you need to undergo during the training. First,
All right. So if I understand the first question is that I've worked on communication and display systems, various space exploration programs, and I guess you want to know some of the work and what I need to undergo. Which I guess that means what kind of training did I get? And so yeah, I've worked in in communication display systems. I've been involved with audio communication systems on space shuttle, and also a specialized audio communication systems called speech recognition, which was actually command and control of the space shuttle space shuttle closed circuit television cameras by voice. And that was rather challenging because it involved the human element to a large extent, which I was not trained for in engineering. I was in engineering. I was trained to, design the best hardware and the software, but never factor the human. But this was my introduction to what we call human factors engineering, and I started to have an appreciation of working with the human element, especially us with the astronauts. I've also worked in communications in terms of displays for the space shuttle, the cockpit avionics upgrade, which was a major upgrade to the shuttle's display system, displaying information about the space shuttle's health, vehicle health overall. And that required actually a lot of electronics, a lot of high speed electronics, which I had some experience with, but that one involved much more than just regular, what I was accustomed to in terms of high-speed communications. And in fact, we had to bring in experts from industry that dealt with high-speed communications and work with us, because it was the first time we've ever sent data rates at that speed on the space shuttle. And because of the nature of the wiring and many other factors, we had to get somebody that knew and understood high speed communication. So it was a very valuable learning lesson. Other areas in display, just as an example, is also right now currently the commercial crew program on SpaceX, as well as the Boeing CST 100 commercial crew program. And as far as SpaceX is concerned, I was involved with the certification of the display touchscreens that SpaceX uses, and that's the first time touchscreen technology has ever been used in space. And that was a major challenge in itself, simply because of the commercial parts had to be qualified for space applications, and there were many challenges associated with that, and not just the environment per se, but also dealing with touch technology. There's some challenges in touch technology. It's not as simple as you would think. We're so accustomed to it here on Earth, and touch technology, uh, is prone to having false touches, which is something that we don't like to hear about, especially in safety critical applications. And false touches can happen for many reasons. Perhaps there's a crack on the screen, or perhaps there's dirt on the screen that's interpreted as a touch. So we had to work through all that. It was a lot of work, but was able to do it. So. As far as what it took to do all that I've been doing over the years, I can tell you that my engineering training at school was just the tip of the iceberg, as they say. Very fundamental. The real learning happened when I started to work at NASA and started to learn what it really takes to develop spacecraft systems. And that's something that's, for the most part, not usually taught in schools, maybe in your master's or PhD program. But even so, you have to learn it on the job. And that's something I tell students, is that you really don't learn, your area very well until you start working. So hopefully that answers that question. Sorry for the long answer.
our next question is, You have worked as a systems engineer and was one of those in developing the internal audio system of ISS as well as many space shuttles. Please throw some light on the internal audio systems of ISS and space shuttles.
Okay, so the audio systems for space shuttle, and the question is regarding the audio systems on space shuttle and space station, and they were actually quite different. Of course, the the thing about the space shuttle audio system, it's much older technology. It's basically late 1960s, 1970 technology. And the company that developed that technology called Telephonics, they developed at that time, it was kind of the state of the art audio systems, but they were not digital. They were more of analog type systems. And so there were some challenges dealing with audio noise and audio dropouts and things of that sort, crosstalk, echoing effects, and so we had to every time we had something new come up, we had to address what the issue was. Now, space station was different. Space station was a digital system. In fact, space station was the first spacecraft ever to use fiber optics. The backbone, if you will, of the internal audio system was fiber optics, operating at a certain speed for handling up to 32 communication channels on space station. So the technology was much newer. But there again, there were some challenges associated with space station audio system. But I do have to say that the major one was more so dealing with fiber optics and radiation, the effects of radiation on fiber optics, because what happens over time is that the radiation tends to darken the fiber optics. And if the fiber optic starts to darken, the I guess the term is light intensity starts to degrade, and so the signals start to degrade. But we were able to overcome the issues associated with that, and now space station's been flying for over 20 years. We've had some audio issues, especially the internal audio controller. The way the station audio system is configured is that there's kind of like a central switching network, if you will. They call it the internal audio controller. And the internal audio controller talks to these audio terminal units that are located throughout space station. And so it basically switches channels from to one end of the station to the other, from station to space to ground, or from space station to the extra vehicle activities. But all that is digital, so much newer technology. I have to say that the technology, because of the nature of it, was a little bit more resistant toward radiation effects, and so was space shuttle. As we start using more of this higher technology, it's becoming harder and harder to certify for the radiation environment, because the newer technology is more prone for radiation upsets and radiation effects, as we call it. So that's one of our biggest challenges. Once we go outside of the Earth's magnetic field, which the space station is protected from, it becomes even harder, and so we have to deal with radiation hardening of components, or radiation tolerant of components. It gets very expensive, and at the same time, it takes more time to develop those kind of systems. So, but those are some of the challenges, especially now that we're going back to the moon. We have to be thinking about all that. And I've recently been involved with the human lander system, and that's some of the challenges we have, is certifying some of this higher, newer technology for deep space activities, or deep space missions.
You have worked on the SpaceX Dragon vehicle, which is very much in discussion currently. So, can you let us know your experience working there and what actually was your task in it?
Okay, so yeah, working SpaceX Dragon vehicle, and share my experiences working with SpaceX, and and what was my task. So, SpaceX and the Boeing CST-100, as well as Blue Origin, all these commercial space companies are under a contract, what we call a commercial crew space program. So that commercial crew space program is basically NASA. Um, Providing contracts to commercial companies like SpaceX and saying we want you to deliver a um, a, uh, a spacecraft that delivers humans to space station, and this is what we're going to pay you, and we're not going to pay you a penny more. And so those are kind of the contracts that these commercial partners have to be thinking about. And because they don't want to spend or go into spending more money than they have to, they're very efficient with how they develop their processes. So one of the things that I noticed working with SpaceX is they have very efficient processes in place. I learned a lot from SpaceX in working being more efficient. And of course, rightly so, because commercial companies are in the business of making money as opposed to the government, which I belong to. The government is kind of like in the business of spending money. So we're just the opposite of commercial companies. And so they try to be as efficient as they can and try to avoid cost overruns and things of that sort. So my experience with SpaceX is, I find them to be very efficient, but they're very receptive to changes and ideas. Now, in terms of my involvement with them, I was the displays and control subsystem manager on the NASA side, representing NASA, working with the commercial crew program. So my responsibilities was making sure that we went through all the verification testing, environmental testing, reviewing the data, looking at the issues and trying to solve the problems. I also support the missions. Every time we've flown a commercial crew program with humans, like for example, Demo 2 in the summer and Crew 1 in the fall time, I'm at Mission Control, which the room is called the Commercial Crew Engineering Support Room, or CSER as we call it. And so I provide real time support in looking at the data coming from the displays and control system that to see if there's any issues. So my support has been from design, development, all the way to mission support.
So, currently, space exploration and Mars colonization are a very, very hot topics going on the space sector. So, being an expert in systems engineering and communication, what infrastructure is required for this to be possible specifically in your department?
Okay, so space exploration, Mars colonization, going back to the moon are very hot topics right now. And my experience in systems engineering, in terms of infrastructures required to make let's see, required for this to be possible. Specifically in my department. So my department basically is the avionics systems division, and so my division is made up of different areas: communications, human interfaces. Let's see what else: intelligent, autonomous. Control, communications, disruptive networks, but then we also have other areas involved in my directorate, engineering directorate, dealing with power and propulsion, uh, in situ resource utilization, which basically is taking soil and getting water off of it. And so there are many different pieces that are associated with developing an infrastructure, and it's not trivial. It's not trivial by any means. And people say, you hear about Elon Musk wanting to send 1 million people to Mars to colonize it and all that. And a lot of us at NASA kind of shake our heads because we're struggling trying to figure out how to keep 4 humans alive for 3 years on Mars. It takes a lot of water, it takes a lot of food just to keep 4 people alive. And so we need to figure out how that's going to happen. And so, as far as the systems engineering is concerned, is that uh, part of systems engineering is looking at trade, what we call trade spaces and trade studies of architectures. And these architectures are basically perhaps design options, if you will, that can support a crew of four on Mars for a long period of time. Uh, but we have challenges in terms of technology. So we got some technology that's capable of doing that, but it's not so good in working in the heavy ion, heavy radiation environment of the moon and Mars. So we don't know how long that kind of stuff is going to last over a period of time. I mean, we can do some estimations based on a lot of testing that we do here on Earth, but sometimes what we do here on Earth and what happens in space sometimes are a little bit different. And so we're going to have to gather that kind of data, data in terms of reliability, in terms of sustainment. Okay, we're going to have to design these systems that are easy to repair, but they're going to be very complicated. So how do you design a complicated system that's easy to repair? It's not trivial, especially when you got astronauts. You only got four astronauts, and they say, "Well, let's use robotics." Well, you can use robotics, but robotics is just part of the solution. We don't know yet how to deal with telerobotics on the moon. We've done it to Mars to some extent, with the Mars Science Laboratory now with the Perseverance that just landed on Mars. But there's still many unanswered questions. And the only way we're going to get these answers is by going to the moon, which is not too far away, just a 3-day drive, if you will, using a rocket and learning to live on another planet. And the example I tell students is that if you want to go to Mount Everest to climb, the Mount Everest, you don't train 1 week before by camping in the back of your house, and maybe it's nice weather and everything, and then you say, okay, I'm ready to go to Mount Everest, where it's minus 40 degrees Celsius, and you're climbing where the air is very thin, hazardous conditions, winds are blowing. You could get blown off the mountain. You don't know these kind of things, and so we have to learn to live on another planet and do it well before we go on to Mars. And so that's part of systems engineering, is to develop that infrastructure through what we call the iterative design process. We design a little, test, find out what's deficient or what we need more, design again, and then test again, design, test, design, test. It's very iterative.
I personally was much amazed and excited at the same time seeing the mentioning of Orion exploration vehicle. So can you let us know about your task on Orion vehicle?
Yes, the Orion exploration vehicle. All right, so I was involved with Orion for a while on the displacement control system until I got put on the commercial crew program. But Orion is really the first vehicle that is being designed for going beyond Earth orbit, and eventually that vehicle will take humans to Mars, hopefully one day. Now, the Orion exploration vehicle is being built in what we call block increments. What does that mean? It means that our first Orion spacecraft is going to be designed, built to test out. We need to test out many kinds of technologies that will be used for an exploration vehicle that's going to take us into deep space. The first mission is going to be what we call the Artemis 1. Artemis 1 is going to be a unmanned spacecraft that's going to go to the moon. It's going to stay there for about 22, 24 days, orbiting the moon. And then it's going to come back to Earth, and then re-enter the Earth's atmosphere and land and all that. And we're going to check out the systems to see how they are. We're going to be testing the thermal tile systems on the Orion vehicle, because this Orion vehicle is going to be coming in very fast through the Earth's atmosphere. So we got to make sure that it protects the astronauts in terms of the hot temperatures as it re-enters the Earth's atmosphere. And then we're going to be testing out some communications systems, as well as some electronic systems, as I mentioned previously, that are related to radiation effects. So we got to test all that stuff out. Now, if everything works out okay, then the next mission, Artemis 2, is going to take humans to Mars, but I'm sorry, to the moon. But they're not going to land. They're going to orbit around the Earth. They're going to check out the systems. They're going to see, how we're going to prepare for actually Artemis 3, which will be the third mission, and that Orion vehicle is basically going to be part of Gateway. Gateway is going to be kind of like the orbiting space station. So they're going to be building Gateway in parallel with this Orion exploration vehicle. So one day, maybe Artemis 3 or Artemis 4, the Orion vehicle is going to dock with Gateway. And then there's going to be what we call the human lander system that's going to be attached to the Gateway space station, and it's going to deorbit and land on the moon, kind of like the Apollo 11. And astronauts are going to get out, walk around, do some exploration, and then they're going to get back on the human lander system, and then come back to the Gateway. And so they'll be doing this back and forth, learning what we call mission operations, because there's so many things that we need to learn about how we're going to operate in this new environment of what we call sustainment missions, where we're going to be there on the moon for a long period of time. The Apollo program, we had a total of 12 people that landed and walked on the moon. But if you include all the time that was accumulated being on the surface of the moon with all the astronauts, it was only about 11 days, okay, total. So we're going to be going way beyond 11 days. We're talking months, years, to be there. And so we have to learn again to live and learn to operate on another planet for a long period of time. And hopefully we don't have so many breakdowns that it makes it very challenging to deal with sustainment. I can tell you that station, it's a major challenge just to try to keep station operating. We got 3 or 4 astronauts. Usually, we have 3 to 4 astronauts on station, but they spend most of their time doing repair work. Very little science, because they're always trying to fix something on station. And you cannot do that if you want to do some real science and real exploration. So that's a big challenge.
You were even involved in many education outreach programs. Please share your experience of those. And we are also an emerging outreach organization. So, what word of guidance do you want to give us?
Yeah, I have to tell you that where I am right now in my career, I really enjoy the education outreach program. It's basically giving back to students and helping them become better engineers, or students in general. And so, I've been doing this now for outreach for many, many years now. And I have to say that the benefit, the enjoyment that I get out of this is knowing that I'm helping students become better engineers. Gosh, there's so many programs I'm involved with. Let me just share one with you for an example. There's something called the Texas Space Grant Design Challenge. So that's a design challenge here in the state of Texas. And so in the state of Texas, there's a city by the name of Austin, Texas. It's the capital of Texas. And the university there, very big university, gets money from NASA to give money to students to work on projects, to learn about what it takes to be on a team in developing a real world problem. And so my responsibility is I'm the NASA Johnson Space Center lead for that design challenge. And so what I do is I go around basically talking to engineers at NASA, Johnson Space Center here in Houston, and asking them to give me some problems to solve, real problems, not book problems. These are real problems that they have that they don't have time for. And so I put those problems together and submit to the university, and then the university gets teams from different schools, and the schools put together a team of students to solve that problem. And so the problems that I usually submit, usually there's about a total of 30 design problems. I usually submit about five. And but for every team that I have, I tell them that it's not so much, how you come across designing the problem. I just want to make sure that you design the problem, approach the problem correctly, that you learn how to solve engineering problems. Something that was not taught in school. In school, they say, they give you homework problems in the back of the book, and they say, design this circuit to amplify a signal. Design this bridge, this little bridge to carry a 10-pound weight over it or whatever. Very small problems. The real world, big problems. And so, these problems involve many different disciplines: mechanical systems, computer systems, um, programming systems, all different kinds of systems, even human systems in general, human factors engineering, dealing with the human element, which itself is a system. People, you don't realize this, but a human is actually is a system in itself. And so, we got input output capabilities. Input comes in from our eyes and our ears, and output is our hands, where we touch screens and we send command and control. So we're really a system. The problem with humans is that we got a lot of problems. we create, sometimes we make a lot of errors or mistakes, right? And so we have capabilities and limitations that we have to know about in order to design a system to avoid those kind of errors. And so that's what I also I try to share with students. So my experience and guidance with students is that I'm trying to help them learn more beyond what they're learning in school. And as far as words of guidance that I tell students is that when you start working, that there's there are two important things that you need to know. Absolutely. One is know who to ask. Okay, you're not going to know everything. I don't care if you were a straight A student in school, that you excelled in everything. You're not going to know everything. And so, I call it the ego trip, right? You think you know everything, but you really don't, and that's dangerous. I was involved with one project where the engineer thought he knew everything, and he kept quiet, that he couldn't solve the problem. But it was too late by the time we found out that he couldn't solve the problem, and it cost NASA quite a bit of time and money because of that. So I tell them, know who to ask if you don't know. The second thing is know where to look. Okay, you need to find out where to look for information. That's something that helped me when I first started, because I didn't know about vibration or the thermal effects of. I took thermodynamics in school, but the professor was teaching it like he wanted us to be uh, research scientists in thermodynamics. And I can appreciate some people want to go into research, but I'm a hands-on type person. I want to apply things to build things. That's what I enjoy, and most students want that. So I tell them, know where to look for that information and know who to ask. And then also is to become a life learner. So much to learn, and so little time. I thought I was just going to stay in electronics because I was a electrical engineering graduate, but I started to learn about systems engineering, and now I'm learning about human systems. So it's been a progression for me in learning, all related to space exploration, but a lot of this applies also to automotive and aeronautics as well. So I tell them, to be a learner, lifelong learner, become a critical thinker, and then I also tell them about not just learning technical skills, but learning the soft skills, learning to work with people, because it's really people that make the project successful. You can have the best technical tools, the best design tools, and all that, but if people cannot get along with each other, and I've been on projects where I had very smart people on projects, but they quit because they can't get along with somebody else. And so you lose that kind of talent. And so you have to learn how to operate with these people. And so the soft skills I find as equal or sometimes even more important than technical skills. So that's something else that I'm instilling on students, is to be, learn about leadership, learning about negotiations, learn about communication skill, both oral and written. I can tell you, just about maybe 2 days ago, I got a email from a student that I had been helping, trying to get a internship job at NASA. He didn't get one, but he got one at a company that supports NASA, and he said that uh, that the interviewer, they call him the recruiter, was impressed with him because he shared with him some of the things that he dealt with working with people. And this student didn't put it on his resume that he had done volunteer work, helping homeless people, people with no food. That he had done some he had worked in a company where he was. It was a hamburger place where he was kind of like leading a team of four at night making hamburgers. But he said, "I that's not." He said, "I didn't put that in there because it's not technical." I said, "No, you got to put in there because it says something about you. It says that you work with people. Companies are looking for uh, employees that know how to work with people." And so, anyway, he got an internship because of that. So I was very thankful for that. So working with people, soft skills, knowing who to ask, knowing where to look, to me, are things that I share with students.
So, you are associated in development of space shuttles since long back and have seen the shuttles evolve. You must have seen new technologies being implemented, and now we have a capsule that is the Dragon Q vehicle. Please describe your views on these mind blowing innovations.
Oh wow, yeah, going from space shuttle to Dragon, it's a big difference. And of course, the thing that obviously comes to mind is uh, the um, the technology that has evolved over the years. I mean, again, space shuttle was the technology was developed from technology from the '60s to to the early '70s. You got to keep in mind that back then, um computers, microprocessors, microcontrollers did not exist. They had to make their own out of independent components, and gates, or gates, not gates. All these kind of gates had to be put together to create a little computer system. And of course, the first computer that came out, it was called the 1802 4-bit microprocessor, and they were able to do a lot of things with that. Um, but still, it was still very challenging. The displays were made out of cathode ray tubes, very heavy. They were not thin screen displays like we have right now on for our computers. They were like 50 pounds just for a very small one. And so the whole thing about technology evolution has dramatically changed how spacecrafts are designed. Software is becoming such a big thing now that it's really one of the critical items that NASA looks at now in terms of developing systems, because uh, again, software can have a certain behavior, but it can also have a misbehavior that we always have to be cautious about. I have to say that the space shuttle did not have a lot of autonomy built into it. In other words, things that were done automatic. A lot of it the astronauts did, or mission control did on the ground. Of course, mission control could send a command that only took 250 milliseconds to get to the space shuttle. Same thing with station. With Dragon, technology so far advanced now. I mean, the computing power is just 10 to 20 times, even 30 times more than space shuttle. And that now we got touchscreen displays. The Dragon is pretty much an automatic system. Everything, it pretty much runs automatic. They got a display system. Not you have I don't know if you've seen this or not, but right below the three touch screens that you see, those three blue displays, right below there's a panel that's used for emergency procedures, and it's got touch buttons. These are tactile buttons, and each one of those buttons performs an emergency function. In the case the software goes bad or something goes bad, they can punch that button. Like, for example, there's one command that's used for cutting the main parachutes. Okay, so if the software does not cut the main parachutes at a particular time, they get a warning message saying, parachutes did not cut, and so there's a button that they manually punch that goes directly to the cutters and cuts the parachutes. But that's part of the safety systems that are built into these kind of spacecrafts. So again, space shuttle, old technology. That's why probably we had 2,500 switches on space shuttle. And it's incredible how many switches space shuttle had, as opposed to SpaceX that has very few switches, but a lot of it is in the software. So a lot more emphasis on software, but that means that we have to be more, what's the word, cautious when we're developing software and testing software. We've got to test a lot of the software, but we cannot test all possibilities of software. If you look at permutations and combinations associated with testing software, it could take years. Giving an example, Voyager 1. The Voyager 1 didn't have a whole lot of software compared to, let's say, SpaceX, but to test every possibility of Voyager 1 software would take 55 years. Okay. So it just takes a long time to test all the possibilities of software. So what do? You test only critical aspects of the software. That's part of systems engineering.
Young group of viewers who wants to become successful scientists like you, work on challenging projects and contribute to space exploration. What would you like to dedicate to them as your word of motivation?
Okay, so again, as I mentioned, that I enjoy outreaching to students and helping them. I've done outreach in India, Africa, South America, pretty much all over the world. But I have to say that the motivation that I tell them is to never give up, and that I don't like to use the word failure that much, because failure means you stop trying. And until you stop trying, you have not failed. You've just suffered setbacks. And so, whether you want to be a scientist or an engineer, if you want to come work for NASA and let's say you live in India, it's possible. I know a lady in India that I met 5 years ago that she wanted to come work at NASA, and I'm going to shorten the story, but I think she graduated from New Delhi or somewhere there, and I told her it's going to take years, and she says, "I don't care, just tell me what I need to do." And so right now she's working on her PhD in machine learning at San Diego State University in California, and she thinks she found a professor that works with NASA, and that's what I told her. You need to come work. You come here, work with a professor that works with NASA, so that way you become known to the NASA people. That your capabilities are to to become a NASA engineer. And so she's doing that. It's taking her now probably 5 to 7 years now, but she set herself on that goal, and by golly, she's going to do it. So the my motivation to the students and inspiration, if you will, is set yourself a goal and don't stop until you get to that goal, whatever it's going to take. You're going to suffer setbacks, but until you stop trying, you have not failed.